Our next presenter is György Pirok. He is a PhD chemist, organic chemist, actually, and he studied right over in that building across the way at the University of Budapest, the technical university there. And he's our CTO, our Chief Technical Officer of ChemAxon. He's been working with us for about 8 years, the past 8 years. His presentation is going to be on virtual reaction design, basically how to get your pile of chemicals and produce a list of the synthetically feasible products. So, without any further ado, György.
So welcome everyone. It's so good to see so many people here in this UGM, more and more every year, and I'm happy to see many familiar faces. So actually, I would start with a question, because there are many familiar faces. I suppose that many of you have seen Reactor running. Who hasn't seen Reactor application demonstration before? 1, 2, 3. Not too many, so I will take it. I will be very short, but will not ignore it completely. But this time, I would like to talk to you about some traps and of the reaction design. Time by time, we get some reports and requests that my reaction is not working, and sometimes the reactions are tricky. But in many cases, the reaction design is tricky, so you have to follow some basic things, and you can avoid most of the issues. Actually, compound enumeration is a way to create molecules which are not synthesized yet, not in your database, but you can make them. One kind of enumeration is Marcus-based, and yesterday, during the technical training, you could play with that in the scope of one technical training. In this case, you generate a CombiChem not a CombiChem library, it's a library of similar molecules where the ligands are different, but they are homologs, and the synthetic pathway is not the way how the enumeration works. Generic reactions is a different approach, provide a different approach to enumerate libraries. And in this case, the enumeration follows a kind of synthetic way, a reaction-based way. Here you can see, right? Maybe this one. Here you can see a generic reaction schema, very simple. An amine is acylated with an acid halide, and the hydrogen halide is eliminated. This is how I think a chemist can perceive this reaction schema. This is actually a click reaction. That's so very simple, probably not many side reactions, but 100% yield and so on. If you add this generic schema to an enumeration to a virtual reaction tool like Reactor, you usually see a kind of mapping, numbers here. So this is the number 1, carbon here. So this carbon is connected to the nitrogen here, to the nitrogen, and the carbon is connected to the nitrogen as well. In this case, it's very simple. We can figure it out. But in some cases, reaction, which carbon went where, which oxygen was replaced, is ambiguous. So this mapping is required to be completely unambiguous where the transformation takes place. If this is missing, Reactor and our software tool try to map automatically the reactions. But since the situation is not always unambiguous, it's always do it beforehand. So one thing, if you experience something strange, map it yourself. The other is, if we run this reaction with simple molecules like isopropylamine and benzoyl chloride, you will get the expected product, and with this other example as well. However, if you just have even a selected library of reagents, you might get some strange products. So this is what we could expect from this nitro compound that we would like to isolate here, but actually the software isolates this nitrogen as well, and also the nitro group nitrogen. Why? Because we didn't mention the hydrogens. So if I go back to this first generic slide, we can see sometimes here NH2, or if the visual settings in the editorial, like in Marvin, is do not show implicit hydrogens, you have a nitrogen here. And it explains this is a query. So the software uses this substructure as a query and tries to find a carbon with a nitrogen in this molecule. And it finds 1, 2, 3 carbon with the nitrogen. Implicit hydrogens do not matter. They shouldn't be displayed. In Reactor software, they are turned off intentionally. So you should add the hydrogens are similar atom to all of the others. So if they are moving, disappearing, or appearing in a reaction schema, you should explicitly define them. So I left this hydrogen, implicit hydrogen here, just to show that these are different in case of queries and in case of generic reactions. In case of molecules, it doesn't matter. It's just a visualization thing. So if you add the hydrogen here, which just left with in the form of hydrogen halide, is the same hydrogen or a different, I don't care now. We just get the expected reaction. Because this nitrogen don't have a hydrogen to eliminate here neither. So a quite large number of reports are related to the hydrogens. Other typical problem is that, okay, I have a nice reaction, it runs, but I would like to oscillate with acid. It's not just acid chloride, but acid bromide as well. And alcohols too, they behave absolutely the same way than amines in this case in this reaction. So my reaction is I just don't get anything. And the other problem is that we have non-analogues. This is an amide here. Actually, there's a carbonyl here, and it became acylated, and I don't want it. So sometimes analog functional groups do not react, and non-analogues react. So how can we make, when we would like to extend the reaction, how can we make it more generic? So we have many query properties in Marvin, like list atoms, with L means list atom. This can be nitrogen or oxygen with a hydrogen, so NH or OH. You can have hydrogen count or many other ways to extend it. And I can here use a list atom or a generic atom type of halogen. So this reaction schema will process both the amines and both the alcohols. So I have a more generic reaction schema. However, this is the one that it is, we have to make it less generic, not to react with all kinds of nitrogen with the hydrogen. So I want amines, but I do not want amides. How to specify that something is not an amide, but an amine? There are several ways in your armory. One is the R groups. It's coming from the MDL word. You can place here an R group. You can draw that it is an oxygen, for example, or a heteroatom with any bond, if you want to be more specific with double bond. And you have to set that the occurrence of this R1 is 0. But this is not too intuitive, because I can see that something is here, which is not. So if I watch this reaction, I do not expect that this part is missing while the others are there. This method works anyway, so you can use it, but if you give it to the hands of other chemists, they will turn to you that what the hell is this, why is it working like that? The other method is using smarts. Smarts are wonderful. It's a wonderful, very flexible language. And absolutely not for humans, especially not for chemists. I even had problems with smiles when I joined ChemAxon. Chemists do not know smiles, not even smarts. This works as well. I can add that this is a nitrogen or oxygen atom, which is not a nitrogen or oxygen atom which is connected to a heteroatom with any type of bonds. So this is the same expression, very ugly. You will be asked to explain what is it here. But if I run this, in this case from a command line tool, I will get the expected result, only one molecule, and not the amide is not acylated. So we are trying to figure out easier ways. So specifying something which is not there is always difficult. So what we have currently is that for each reaction, here is the generic schema, we can have an expression. We can have here the smarts, that it's not matching a nitrogen and oxygen, not connected to heteroatom. Or we have a dictionary, we can say that this atom, reactant atom with the map number 2, so this is here, is an amine or an alcohol, an amine nitrogen or an alcohol oxygen. So we can refer to the names of the structures. So this is a bit simpler probably than smarts. I'm not saying that it's intuitive. You have to understand the rules and you have to learn how to formulate these things in chemical terms. But it works as well. We will get only the expected acylation. How can we make it more simple? This is something which is not yet done. But we are thinking of specifying this kind of functional groups just right on the schema. This seems for me the simplest. Do you agree with that? Okay. If you agree, we will do it. So hands up. Who would like to have this kind of simplification? Okay. Who wouldn't like it? The rest are shy. Okay. Oh, thank you. Okay, will you have a presentation? Okay. So we are working on make it more easily to formulate these queries, and this would work in queries as well. So now the part which is reactor. We have a software called Reactor which can process starting compounds with either of the ways what I showed before, with R groups, with smarts, with this kind of rules to products. This will be very quick because I each year show Reactor, but this will be very quick. Here I opened Reactor in a wizard application. We have lots of applications of the same engine. And I selected one reaction from a library. You can have your own reactions. It's a Friedel-Crafts acylation substituting a hydrogen of the aromatic carbon. Okay. I press next. I can load some reactants from an example file. Benzene, indole, anthracene, nitrobenzene, bromobenzene, acid halides. I have to specify an output. That will do. And I will generate fused reactions. This is a new option. We can generate fused reactions, and the new option is here that you can have an excess of a reagent in reactions, so you can multi-substitute molecules in the new version. And I just turn off everything, only the generic schema is here. So what we get is are 5 reactions. Benzene is acylated. indole everywhere. You see a carbon, with aromatic carbon with a hydrogen. There are lots of. So we are not happy with this set of products. Anthracene everywhere. The symmetric isomers are just, no, not isomers. The symmetric drawings are just filtered out. Nitrobenzene reacts everywhere. Nitro group deactivates the ring. So we should know it. Bromobenzene is acylated everywhere. Ortho meta para. If I turn on something within this reaction, some rules, then the resulting set will be nicer according to our taste. Indole at the 3rd position, antacid at the 9th position, bromobenzene give ortho and para. So this was a reactor, and what I wanted to demonstrate only is that it can generate feasible reactions, feasible products, if your reactions are feasible, because our software doesn't know chemistry. We neither. However, chemists know it. So what we wanted to create is a software which the chemists can include the rules. You know, the old professors watching your presentation in the university and telling you, I don't understand why you did in this way, because you should have known that those too many aromatics will make your entire reaction rotten. So if someone can tell this, we want to give a software in which you can include this knowledge, put it within the reaction. A reaction is a compact thing, so you can add some rules. One rule is called reactivity. So in case of nitrobenzene in the Friedel-Crafts, nitro deactivates the ring. And this cannot be a structural kind of condition, because there are lots of activating and deactivating substituents. Even an acyl group deactivates. So we should calculate something, and we just notice that if we calculate the sum of partial charges on the ring which is reacting, and if it is more positive than minus 0.2, according to our calculation, it separates nicely the active and deactivated rings. So we can use it to make the reaction more feasible, and it calculates the sum of partial charges on the ring of reactant atom 1, which is actually here, this aromatic carbon, and will not produce any Friedel-Crafts products in this reaction. Let's choose another reaction, because we are always talking about Friedel-Crafts, because it's like a medical animal, so has all the diseases and features what we can demonstrate, but let's change it now. Here is Baeyer-Williger oxidation, where we put an oxygen between a carbonyl and a neighboring carbon, but it has two sides. It's okay, it's not the question whether it's active or not active. This is another non-structural condition, which is in the selectivity rule of the reaction. We calculate the partial charge again here, but the sigma partial charge for R atom 2, which is this one, actually matching both sides here. And we sort all of the reaction sites in the molecule by this expression. So there is no equation or something, it's just a value. And the one on the top will lead to the main product. So in this reaction, we found that partial charge calculation is a simple way to choose. It's like a kind of Markovnikov rule. There are more substituents. The oxygen prefers that side, but it depends also on this is okay in case of carbon, but you have electron drawing and sending groups. It may vary. So this partial charge calculation drives this reaction well. So our second rule is selectivity. Reactivity refines the reaction site, activation, deactivation. Selectivity helps you to choose from the many opportunities which will lead to the main product. We got ortho and para in case of the Friedel-Crafts because we used another calculation and had a tolerance as well that the top few ones, which are almost having the same value, are considered leading to the main products, but not matter. The exclude rule is the last one. This is probably usually the largest because molecules can contain lots of other functionalities which can cause side reactions or destroy the catalyst. We just want to exclude them. So exclude rule usually contains lots of structural references. So it shouldn't be an acrylic halide, or shouldn't be NH or OH and so on. But in sometimes you can have a non-structural expression here. For example, the halogenation of olefins, this reaction, it has a side reaction if you have a very small ring. Small rings are opened by the halogens if you do not have UV light, which is usually the case of this halogenation. So we just say that if in case of molecule, when the smallest ring size of reactant 0 is less, oh, a parenthesis is missing, is equal to 3, then just do not choose this bromination reaction, because you will get side byproduct. Reactor comes with many interfaces. Actually, reactor is an engine. It's an API what you can use. And we first developed this reactor wizard, what I demonstrated here. It works with files. You might want to use reactions with the molecules in your databases and want to generate products in your databases. Instant JChem is a very handy tool and for a desktop chemist. And in this case, we have a flattened wizard. It's only one page. You select the reaction schema or you draw it yourself. Select which table contains or which molecule set contains your input molecules and specify the output table, some options, and execute. It is intentionally much simpler than the reactor wizard, which contains the reaction editor. Okay. JChem for Excel, it's beautiful. You can just drag down the cell and you will generate CombiChem products. So it's a very simple way to do some reactions. Usually just have a reaction schema, but here you can scroll down the dialog and you will access all the rules if you want. Nice integrations in Pipeline Pilot as well, and NIME, in which these are quite complex ones, but both include some reactions. And I would like to highlight that in this pipelining software tools, you can directly do multiple syntheses. With Reactor, you just generate the first step, then choose the products to generate the next one. In this case, you can just append more and more reactions after each other. And it is also integrated into JChem web services, so you can access reaction functionalities from PHP or Python, and you can enumerate libraries. Also, it is in JChem cartridge, so you can have SQL statements to execute reactions in Oracle. I can run reactions from my command line tool, and we also have Java and .NET API for developers. So actually, it's available from everywhere. So finally, some features and limitations. Features, chemically feasible reactions if you want, but if you don't, you can use your SMERC, SMARTS, RxM-based enumeration, that's fine. You have to pre-select your reactants. It's not a black box. You can always modify a reaction if you experience something else and create new ones. It is high performance. You can generate huge libraries quickly. Speed depends on the calculations included and on the complexity of your reactions. All property calculations are currently included in Reactor license for within the use in the rules. So you can access all calculations of ChemAxon to make your reaction better. We are currently working as well on the expansion of ChemAxon's reaction library. We will want to cover a much larger set of the tools of the organic chemistry. It is available in many platforms and we provide many applications. Current limitations we are aware of. Some calculations need improvements. You know, these calculations, as we heard, it's it's a cheminformatics. So these are quick and dirty, which are usually provide quite reliable results. But in some cases, like nucleophilicity and things like this, we need some more improvements because, for example, the Hücke rule just didn't consider the effect of methyl substituents, for example. Some calculations can be slow. For example, conformation-based, when you need 3D conformers. Some calculations are not available yet. I would love to have HOMO and LUMO, but I doubt that we can have it in a quick way. So we still have to think about how to solve these issues and so on. Multi-step reaction schemas are not supported yet. So we cannot calculate the properties of the transition states. It's on our development pipeline. It's been there for years. It's always by the next release, but I still hope that we will have it soon. Sometimes we do not have an idea why that is the main product of a reaction. We don't have idea. So in that case, our reaction won't be selective, or we can play with the properties to figure it out, but sometimes it's lack of any science. It's just trial and error method. And some stereo-selectivities are not supported yet, not supported by anyone else. So we support double bond stereo, tetrahedral stereo features. So we have inversion retention. And we just found out how to support prochirality. So this will be coming in I hope in 5.4 release. So you can have reactions which are selective by prochirality. It will be something new. Future reaction. And this is my last slide. New execution mode in reactor, in which you can manually select the products. So it will show all the alternative products if there are more than one, and you can click on that I want in the output. So you can drive it manually if you prefer. We will improve the property calculations, as I mentioned. We are developing new algorithms, for example, some better topological approach for steric hindrance, for example, even if it works only for aromatic reactions, it will improve some of our reactions. The new stereo features, we are reviewing intensively our current reactions in the library. We've found some issues and we are fixing them and doing more validation with experimental data. And we are also adding more and more reactions in the library, so you can expect new sets of reactions in our library. I would like to thank you for your attention, and thanks for all of the ChemAxon people, because development included lots of parts. So the drawing tools, the databases, the web services, property calculations. So I cannot show the entire, maybe I should have a group picture here. However, these ladies and guys are the most directly involved, the ones who were most directly involved in the development. Nora started the reactor engine development, and György took it over. He is working on the prediction plugins as well. Jenő Varga and Anna Tomin are both chemists who are helping us in the development and design of new reactions. Attila Szabó and István Rábel are the developers of the applications of reactor, like the Reactor Wizard, but as I see, many others will be here, and thank you for your attention. So if you have questions.
Thank you, György. That was very enlightening. Is there any questions for György? And in the back here. Sure, Richard.
With your reactivity rules, if you allow exhaustive reactivity, do you take into account the first reaction to decide if a second addition is more or less likely?
Sorry, pardon?
So you've got your chemical reactivity rules.
Yes.
But if you turn on the option that allows exhaustive reaction.
Yes.
So do you take into account the first reaction to decide if... So if you were doing
reverse
nitration,
reactions.
if you were doing a nitration...
Yes.
obviously once you've added one, the second is less. And that, so
Yes.
do you take that into account?
Yes, absolutely. So this is, for example, standardizer replace the standardizer transform, identifies all the matching functionalities, and replace them all. Reactor does it in loops. It's exactly the same what you would do because a reaction changes the properties of the molecule. So what I would expect, so I hope that, for example, the nitration of nitrobenzene, if I have 10 times more nitrous acid, would stop at dinitrobenzene, methyldinitrobenzene. But toluene would go to trinitrobenzene. So that is what we would like to achieve. We are working on this validation of these multiple substituents things, so it's an ongoing process.
So second question, if you don't have homo-lumo, do you predict Diels order regio?
Which one?
If you're doing a Diels order and you want to predict the regio specificity, do you do that?
Well, yes, Diels order reaction. We have Diels order at the moment, but for example, we do not support everything. We use a much simpler method, which works in many cases, but not in the case of others. So the manual method will help you to drive it well. And we do not even have the endo and exo stereochemistry well, so we still have a lot to do in the case of some reactions. So if we will have HOMO and LUMO, it will be a salvation for us for many reactions.
Okay, great. Okay, one more question.
I was just going to say, it seems like you've given us all the tools to build an expert system. I wonder why you don't go the whole hog and get, really train it up and make it a really, invest the time with, I guess you are, but get some collaboration with perhaps a chemistry, academic chemistry organisation and really build up the expert system side of it so that, it'll do
Actually, yes. Actually, we do it in a small way. Actually, those who design the reactions are working for academics, so they are from university and research institutes. But it's not an entire organization. It would be nice. Another nice thing would be to collaborate with a reaction database provider together to make these reactions better and based on the experimental results. We lock the experimental reactions. We don't have a reaction database, but would be very open for such a collaboration. Yeah. So we would like to make it better. So I agree, it would be a good way. Thank you.